Now I think we can move on, and let me tell you what is Light4Lungs about. Who is afraid of the Light4Lungs proposal? That's me, of course. And a quick overview. Let me, if you allow me, let me start with this cartoon. Do you want to take the time to read it? Do you get it? Indeed, science saves lives. That's the message. And of course, there is a big connection with light that makes it even closer to the topic today. So it is our goal as scientists to develop science, to create new knowledge, to disseminate this knowledge. In the end, this is what Light4Lungs try to do. The problem of resistance, I think, has already been highlighted, but let me give you the big numbers according to the World Health Organization. As of currently, we estimate that antimicrobial resistance, that is the no longer working of antibiotics, is causing 700,000 deaths. Okay, but the prospects are terrible, and terrible means that by 2050, it is estimated that antimicrobial resistance will cause like 10 million deaths unless we collectively do something to solve that and address that. Notice that cancer is, the prospects is like 8 million, therefore antimicrobial resistance will be the leading cause of death by 2050 if, as we say, we don't do something to change the trend. There is also an ethical problem that affects us, and that while the Western countries, Europe, North America, even Latin America, are not that affected, if you look carefully at this map, you will see that Asia, and especially Africa, will be most affected by this problem. So in addition to a technical or scientific problem, there is also an ethical problem of not letting these people down when they need us. ESCAPE has been an acronym used very popularly to define the most important pathogens, the bacteria that cause the most infections, the lethal infections. Enterococcus faecium, Staphylococcus aureus, you have heard a lot about it in the previous presentation. Klebsiella pneumoniae also, Acinetobacter baumannii. I think it's better now. I don't know what they did, but sounds better to me now. God bless the technicians, really. Pseudomonas aeruginosa, Enterobacter cocci, and related, and particularly to lung infections and the nasty ones, or cystic fibrosis and hospital-acquired infections, there are two bacteria that pose the major risk, and these are Pseudomonas aeruginosa and Staphylococcus aureus. Therefore, in the Light4Lungs project, we have chosen these two bacteria and several strains, some derived from patients, to develop our medical technology. So let me briefly go back in time and tell you about the uses of light in medicine. When we proposed to use light to heal, this sounds a bit like magic, until you recognize that light means energy, and light can trigger chemical reactions, and those chemical reactions in the end introduce biological changes that ultimately eliminate the pathogenic bacteria. So light in medicine, or the use of light in medicine, was appreciated already by the Egyptians and the old cultures on the earth, and people were exposing the young boys with rickets and other diseases to light to heal them, to treat skin diseases. These are two reliefs that you could see in Egypt. The origin of photobiology as a science is bound to Finsen in Norway. In Norway, that's quite interesting because of the light problems that may have up there, at least in winter, to treat skin diseases, lupus vulgaris, if I recall well. And the photodynamic therapy, well, sorry, this is wrong, that should be 1978, came up to stage when Tom Dougherty in the United States demonstrated that you could use light and some molecules to eliminate cancer cells. The discovery, of course, is earlier, but the application in medicine is from the 70s. So people need to distinguish between phototherapy, photochemotherapy, and photodynamic therapy. And all of them share features in common, but also have their differences. Some of you, or maybe your babies, may have been exposed to blue light after birth to treat the neonatal jaundice, the growth or the accumulation of bilirubin, mesubela bilirrubina, we say in Spanish, but that's essentially the idea, and you treat that kind of disease, by exposing the skin to light, to blue light. This would be phototherapy, and this uses an internal molecule, in this case bilirubin, to act photochemically. The second possibility is to administer a drug and then administer light, deliver light to the lesion, and this is called photochemotherapy. In that event, you simply have two components, light and the drug, and a typical example is used by dermatologists to treat psoriasis and other skin diseases. For instance, the PUVA therapy. Photodynamic therapy is the third member of this group of therapies, and photodynamic therapy includes a third component, which is oxygen. Sorry, these two should be down, but that doesn't really matter. Light, a drug, and oxygen, when the three of them combine, you produce something which is called the photodynamic effect, and the name comes down to Professor von Tapaina in Munich at the onset of the 20th century, where actually he observed that, or a student of him observed that effect by studying precisely the photoinactivation of microorganisms. Since then, photodynamic therapy has evolved, has grown, and it's now used in the clinics, and we are simply proposing an additional treatment that combines this effect. Let me show you the photodynamic effect in action. On the left, you see cancer cells, HeLa cancer cells, which are exposed to a drug. Of course, they are exposed to oxygen, but there is no light. And as you can see, if you look closely, these cells simply reproduce themselves, are happy, just live a normal life, so to say. However, as soon as you switch the light on, you begin to see that there is some processes going on and the cell is destroyed. So this is the photodynamic therapy in action, and again, you need the three components, light, oxygen, and of course a drug that essentially captures the light and activates oxygen, which ultimately kills the bacteria. Are you familiar with the term active oxygen? You have heard that on TV commercials, for instance. Active oxygen makes everything cleaner because it cleans your teeth, it cleans whatever. And active oxygen means an oxygen which is more reactive oxygen species. So the role of light is to activate, to convert the normal oxygen that we are now breathing, so please breathe, to the active oxygen that has such an oxidating power much higher than the one we are breathing. Photodynamic therapy is now being clinically used to treat both cancer lesions, many of them, as well as infections. And there are a number of applications which are already being approved by the regulatory agencies, and others which are undergoing clinical trials. And if you go to clinicaltrials.gov, and you enter photodynamic therapy, you will see that more than 200 clinical trials are currently underway to explore different applications of this effect. But the problem is that you need three components: photoactive drug, oxygen, light, to produce reactive oxygen species, which ultimately will kill the bacteria. The beauty and the Achilles heel of photodynamic therapy is that it has no target, unlike conventional drugs, in which you have one drug, one target, and the cell, the bacteria, can develop easily resistance against that drug. In photodynamic therapy, The mechanism of cell death is very simple, oxidation. And there are lots of oxidizable targets in a cell. You can destroy the cell wall, you can destroy the membranes, you can destroy the ribosomes, you can destroy the RNAs. So there are so many targets that it's not really possible for the bacteria to develop resistance, to protect all of them at the same time. That's the beauty. The problem, therefore, is that this happens in the pathogenic bacteria, but this also happens in the normal cells. And therefore, you need some degree of selectivity to engineer some selective delivery system in order to target the cells you are trying to eliminate. So, the good news, photodynamic therapy works. It can eliminate bacteria. Second good news, it works irrespective of the resistance profile of the bacteria. So when you treat normal bacteria and wild-type bacteria and antibiotic-resistant bacteria, you essentially find no differences. So the photodynamic therapy overcomes the resistance of bacteria to antibiotics, and this is the very good news. And the third good news is that it does not induce resistance. There are some reports on some tolerance, but in the end, you kill the bacteria. You inactivate and eliminate those bacteria. So this is working, and this is useful and worth exploring the possibilities. So can we do photodynamic therapy in the lungs? You have seen in the previous talk that essentially the lung tissue is covered with this mucus and the biofilms of these bacteria, and that's difficult to deliver the drug there, the antibiotic there. Therefore, the question whether it's better to target it from the inside, systemic, or from the outside using an aerosol. It's difficult. Oxygen is there, that's the good news. That's the good news. But we need the photosensitizer, we need to deliver the light. And something that you may have seen is that red light, and this is very tiny pointer you see now, really goes through human tissue. Can you see my finger, red, of course? If I would do the same experiment with blue or green or other colors, you would see absolutely nothing. However, red light can come through. So we could put red light on the chest and illuminate the lungs from the outside. However, because of scattering and other effects, not much light would reach the interior of the lungs and all the ultimate alveoli and small compartments inside. So what we think is that, of course, you could insert some fiber optics, like a bronchoscope, for instance, but as you can imagine, this is very, very invasive. Not only that requires hospitalization, plus it is not guaranteed that you can reach the ultimate alveoli, and so all the corners inside of the lungs. So it's difficult to send the light first. It is also very difficult to send the photodynamic effect to the lungs because of classical transport and delivery phenomena. It is difficult to send the light, and it's very invasive, so we need a different approach. So the big question is, can we streamline photodynamic therapy, simplifying the therapy? 3 components: oxygen in the lungs, we don't need to care about it normally. Light and the photosensitizer, the molecule that will capture the light and activate oxygen for us. And here is the concept of Light4Lungs. The simplest way to deliver light to inside the lungs is to use a nano lantern, a nanoparticle that emits light without being connected, tethered to any battery, I mean just the nanoparticle itself. And that nanoparticle can be inhaled, will be, depending on its size, will be distributed throughout the lung, and by the time this particle is residing, is inside the lungs, it will deliver its cargo of photons. And those photons ought to be enough, of course, to treat the lungs. The third component, the photosensitizer. We use the biological machinery in the bacteria to convert normal oxygen into active oxygen. And here is the trick. In bacteria, in your blood also, you have molecules able to capture light, able to activate oxygen. We have hemoglobin. Hemoglobin is not the molecule, don't be afraid, not yet. But we do have hemoglobin and other compounds that can absorb light. And one of those molecules is called protoporphyrin. It's a precursor of hemoglobin, but protoporphyrin has the ability to activate oxygen. Therefore, what we do is to try to use the tiny amounts of protoporphyrin that bacteria have inside to use that tiny amount to activate oxygen. So therefore, it's like saying that the bacteria create their own drug, and we are simply exploiting that drug. Normally, the inside of the lungs are not reached by light, but if we would put light there, we could use that tiny amount of protoporphyrin to activate oxygen and kill the bacteria from the inside. Trojan horse would be a good simile, a good idea, a good image of what we are trying to do. This is exactly the idea. So what we do, and you will hear the technical details on this in the second part of this morning meeting, we have prepared particles. Those particles can be activated in the form first of an aerosol being prepared. After preparing the aerosol, we activate these particles in the aerosol, so from that moment on, they begin to emit light, and then we use a nebulizer to deliver these activated particles, light-emitting particles, to the lungs, therefore delivering their cargo of photons afterwards. If the particles are small enough, they will come in and come out. If the particles are larger, some of them will reside in the lungs, and then we know that they will be eliminated by the macrophages there, and this is one of the experiments that you will hear later on. So, ideally, that should lead to bacterial cell death inside of the lungs using light. So we are simplifying the therapy in that we are not using light delivery systems such as fiber optics, and we are not using photosensitizer, that is external drugs which are difficult to deliver to the lungs. So we called the idea of breathing light. Sounds like a weird idea, right? Can we breathe the light? We think we can. And I must say that this was still is live. A FET open project of the European Union, which devotes a lot of money to explore ideas that look like impossible. But if they succeed, and ours has succeeded, might change the paradigms. And this is the idea. Can we breathe light? Something which is not really new. You may be familiar with this kind of toys. You might still have it in your room. Who knows? But you know that in the night you have this kind of paints that glow, and we may have them. Actually, I see them on top of the door. If now the lights would go off, you would see that those signs would light on and lead you out of this room. So safety signs, toys and decoration, this is present. Some people dream of using this kind of markings to mark roads in the night, so that during the day they would be charged, and during the night they would simply mark the limits of the road. So these kind of ideas have been already there, and the question is, can we make those pigments small enough so that we can breathe them? And this is essentially what we have done. So we have developed particles. The material is zirconium oxide doped with titanium. That's already in the literature, and useful in terms of size, in terms of dispersibility, and so on and so forth. So that material is activated by ultraviolet light and emits blue light. I think you can see that. That's a picture, but I think if that video works, not sure it's working. There it is. You see, we are now, that was very quick. Did you see that we were exciting oh, it is there. we excite there, and when we switch the light off, that will happen now in a moment, hopefully. It doesn't happen. Doesn't matter. I think you have captured the moment before. When we switch the activating light off, and that happens outside of the body, the particles keep emitting light for several seconds. Enough to breathe in, deliver the photons, and out. That's about the idea. So the result is that we are eliminating bacteria. That's essentially what we wanted to do, demonstrate that we can do that. And what we have explored is the effect. This is the light dose that we deliver using particles. In that case, these were LEDs. So we explore whether light alone, no drug, no nothing, could be used to photoinactivate bacteria. And what you see is strains that are obtained from patients, from cystic fibrosis patients, the LSB65, correct me if I'm wrong, PA01 in the case of Pseudomonas aeruginosa, but also the USA 300 for Staphylococcus aureus, and a methicillin-resistant Staphylococcus aureus strain derived from cystic fibrosis patients by the Liverpool partner. And what you see is that different colors of light do have different effects. The higher this curve goes, the more effective it is at eliminating bacteria. And you see that violet light, 415 nanometers, is the most effective light to eliminate all the bacteria, followed at some distance by blue, green, and red light as well. Images of the bacteria. What does light do to the bacteria? These are Pseudomonas aeruginosa bacteria. This is electron microscopy pictures, intact. This is what you see a normal bacteria first. After 1 hour exposing those bacteria to blue light, this is what happens. And what you see is like breaking a piece of bread. Doesn't that look like that to you? It's like you're breaking. And essentially, this is what's happening. From the inside, you are killing those bacteria. And of course, after 1 hour, that already happens. After 2 hours, the damage is even more extensive, and we essentially kill the bacteria from the inside. I think these are the last couple of slides of my presentation. We use all these technologies that we chemists use in the laboratory, lasers and other spectroscopy tools, to study what is going on. Understanding what is going on give us clues to improve the parameters, define the parameters that affect the outcome of the therapy. And this is the idea. The very first thing that we did is to study what we call the action spectrum of the therapy. What you saw in a qualitative way, it's now quantitative, taking into account the tissue, diffusion of light, scattering, plus the different wavelengths applied to these biofilms. We saw that the spectrum of action of light, that is, which wavelengths are more effective than others, would find the peak at about 415 nanometers, as we saw. But also, green and red light are less effective, but somewhat effective as well. So this very much reproduces what we observed and give us clues to develop the particles. We need particles that essentially emit light in the violet region. Not ultraviolet, but violet. Once we have that light will simply be absorbed by a substance we call PS, the photosensitizer. The photosensitizer, I mentioned that earlier, is protoporphyrin, a molecule which is inside of the bacteria. And then it will undergo a series of photochemical reactions leading to oxygen activation and therefore ultimately cell death. And the good news is that this is a circle, meaning that at the end of the process, the molecule, the protoporphyrin, is there ready to start yet another cycle. This is catalysis. Essentially, it's called photocatalysis. So very tiny amounts of protoporphyrin can undergo thousands of cycles like this, and each cycle is a therapeutic effect. We found out that the reactive oxygen species responsible for the effect is called singlet oxygen, is one of the activated forms of oxygen. People are familiar with hydrogen peroxide, superoxide radical anion maybe, the hydroxyl radicals, unless people are aware of something called singlet oxygen, which is an electronically excited state of oxygen and happens to be the one species responsible for the effect. And these are pictures that we obtained in the lab that show, that demonstrate that in bacteria, singlet oxygen is produced. So this is the killer. Let me introduce singlet oxygen to you. And once we know that it is singlet oxygen, the species responsible for the effect, then we can go to the literature and find how to increase the effectivity of singlet oxygen. And the literature says that, for instance, among several enhancers, potassium iodide has a synergistic effect with singlet oxygen. And therefore, under conditions where we would see essentially no photokilling of the different strains, Pseudomonas on top, Staph aureus at the bottom, in the presence of potassium iodide, you see a huge increase in the efficiency of the photoinactivation therapy. Meaning that it's not only light, it's not only the compounds in the bacteria, but we can develop a therapeutic process in which other adjuvants need to be added or can be added to improve the outcome of the therapy. And I think that was all, and I leave this question here. And now what? Now we have a coffee break, that's the first idea, but beyond that, now what means that think, we want to consider, we want to listen to people who know what happens next, how we move from the lab to the patient. And this is what will be discussed this afternoon with our panel. In the meantime, though, after the coffee break, I invite you to follow for more technical discussions on the different aspects of the therapy that I have highlighted. Thank you very much for listening. Questions, comments, of course, are more than welcome. Please.
So congratulations, because it looks like I understood everything. So probably is not so simple, but there are many wonderful ideas behind your proposals, and I have many questions that probably will be answered during the next presentation. But my comment is that I'm not working directly on photodynamic therapy, but you have, in some sense, solved the problem of the range of activation of oxygen, reactive oxygen species. Because if I remember well, they are active in a very short distance, a few tenths of nanometers, something like that. So if you can activate them in the cell, in bacteria itself, okay, this is an incredible advantage. So I have just two general questions. First of all, I mean, as you said, you can kill all the bacteria. You cannot discriminate between positive or negative effects. So can you do something to improve this picture? Can you do something to, I mean, at least to develop much more porphyrin in the bacteria that you want to kill, or something like that? This is the first question. Then I have another one about the wavelength that you are using. You are using a wideband emission from 400 up to 550. And I understand that even if the efficiency of light is higher at 415, this is clear, but nevertheless the penetration depth is smaller. That's why you can take advantage also of the other wavelengths, which are more in the green, which has a longer penetration depth. Is it correct?
Yes, there are two questions here. Thank you for the questions. I guess you will get answers, more profound answers to the questions during the rest of the day, but quick answers now would be, yes, we can enhance the content of porphyrins inside of the bacteria. This is one of our enhancers, and you will hear about it later on. There are different ways of doing that, but you will see that it works. And regarding the second question, of course, ideally, we would use, we believe, we wanted light at 415 nanometers, but the materials that emit at that wavelength are not as effective as the materials that emit this broader band emission. Nevertheless, this has advantages because inside of the bacteria, there are several chromophores. And we found, and won't give up any secret, but we found that some of the additional wavelengths have a synergistic effect by activating another chromophore inside of the bacteria. I cannot say more than that, but it is of our advantage. Let me put it this way. Thank you. More questions? Comments? Maybe from online, Ada? Somebody online is asking any question? This is a message for people attending online. You are welcome to ask questions. Do that using the chat, please, so that we can convey them to the speaker.
Santi, it's not a question, but in a response to the previous one of the previous questions, I just wanted to say that when it comes to chronic infections with Pseudomonas aeruginosa, it really does often dominates the microbiome. So over about 90% of the bacteria present would be the target pathogen. And so although I think it would be really, really interesting to understand the impact on the wider microbiome, it is likely that the majority of the bacteria present would be the target pathogen.
This is Joe Fothergill from Liverpool. This is one of our partners. Joe, I was not really sure whether that was a question or a comment.
Mine wasn't a question, it was a response to the previous question about the impact on the other bacteria present.
Thank you for that, Joe. Any more questions? If not, I think we can go to the coffee break. Please, people attending, you will be given a ticket that you can go to the cafeteria and they will give you, you can order coffee or some snacks. Members of the consortium, please, we need to go upstairs. There is something for us. Thank you.